First of all, I would like to give a problem, a matching problem. All right, so let's assume that we have a transmission line here, 50 ohms. And I will assume that this is E0. And then we have a load that connects to this line. And then this load is CL equals, say, to 50 minus J 100 ohms.
We need Smith charts on the exam.
I will provide them electronically. I will have them attached. I will have them on Canvas, not attached. I mean, where you're going to find the homework, you can click and download the Smith chart.
But do we need to like print them and bring them out and use them?
Necessarily, if you can do it on that, if you cannot, I will then have printed out also in class, in case people cannot do the.
Is it open note exam?
What's that?
Is it an open note exam?
Open everything.
Okay.
Yeah, open everything usually. And I will bring also some printed in class. It's good that you asked me this question because usually I don't have anything that I print, but I will print the Smith charts. All right, so let's assume that this has a length L. I develop the problem as we speak. So let's assume that this transmission line has a length L, which is 1.5 lambda. We will assume that Z0 is 50 ohms. We will assume that it's connected to a source which is with ZS also 50 ohms. And the source VS is 1 volt. And then the question will, so this is problem 1. So question A will be to design.
I have a quick question. If you, okay, it's not really like pertaining to this exactly, it's more just generally any question.
Yes.
If we're given the frequency and the wavelength, do we consider like you know how like some equations we use this like the speed, like the phase velocity, I guess.
Yes. In these ones, in the matching circuit design, I'm gonna give, if I give the wavelength in physical lengths, that I will give everything in physical lengths. But if I don't give you the wavelength and I give you a length like here in wavelengths, and I do not give you the wavelength, then practically I will not ask you to give me results in physical lengths. I will ask you to give me the matching network in wavelengths, all of the whatever dimensions. See what I'm saying?
Well, I guess what I'm asking is like in last homework, the only question I guess you gave us the frequency and the wavelength of the
yes.
So
I gave you
the speed didn't multiply to the speed of light. So should in equations, do we use the speed of light or do we use the frequency times the wavelength?
The frequency times the wavelength, because what happens is that in ideal transmission lines is the speed of light. But in microstrip, since I gave you F and lambda, the product of the two is going to give you the phase velocity. If it's microstrip, it's going to be less than the free space velocity.
Okay.
See, so you're gonna, if I give you F and lambda, then, and you need C, you need the, excuse me, the phase velocity, then you get the product of the two.
I see. Okay, thank you. But okay, I have another quick question.
Yeah.
So in the textbook, like the matching network textbook, kind of
Yes.
network theory textbook,
Yes.
on the part where it like had the chart for the different types of
Can
like,
I go there so you can, I can find it? Let me see. Let me go there for a second. So I'm here. This is
Yeah.
the network.
that
See, just a second. So that's classes. Let me find courses. Courses. This one. Smith modules book. Okay, in fact, I'll go to the modules rather. Okay, so which part are you talking about? The matching networks or the networks?
the ABCD parameters.
Okay, so the ABCD, I think it's,
Network theory.pdf.
yeah.
You had it up like earlier.
Yeah, I probably, but I need to use these ones, network theory, because I have removed things, all right?
Okay.
I have removed the things that we're not covering. So, okay, tell me where to go.
It's on page 14.
Okay, it's 14. Yeah.
Yes. So okay, at the top it's like beta times length and theta are electrical lengths of transmission lines in radians.
Yes.
Is theta the length like just of the
It's beta D, is beta times the length of the stub. Theta, let me write here if I can. I don't think I can write, but this theta here that you see, all right, this theta is, or this theta down here, or this theta here.
So those are beta.
These are beta, which is 2 pi over lambda, times D, which is the length of the stub.
Okay. I just want to clarify. Thank you.
Okay. All right, so here you have to design a matching network using a series lumped element at an appropriate position on the transmission line. I'll write all of the questions. Then B, replace this series lumped element with a stub with a let's say short stub, short circuited. Stub and identify its length in terms of lambda. Okay, these two problems. So let's think how to solve. This is an easy one. Maybe I can make it a little more difficult because maybe why do I not solve that and then I will solve a different one. Okay, there's 50. Let's try to solve this. Let me, I will continue. I'm not going to ask you so much. So I can write out the solution. In this particular case, the first thing you have to do is to look at the load. And then you realize that the load, so let me write solution here. So first of all, I make an observation. First, observation. All right, it's important to look carefully at what I'm giving you because sometimes the solutions can be very simple. The first observation is that the real part of ZL is equal to Z naught. Why is this observation important? Because if ZL did not have an imaginary part, then ZL as a load would be only 50 ohms and it would be totally matched to Z naught. So you will not need the matching network, all right? So since this is true, that implies that ZL, we need to find a matching practically. So we need to find, implies that we need to find a matching network, a lambda element. We need to find. So this is still A. We need to find a lambda element that will cancel the reactive part of the load. Okay. Because we want to keep the 50 ohms and we want to eliminate the minus J 100 ohms. What that implies here is that if I take the same picture that I have here, copy, and I put it there, paste, right here, I can place, and here I will include it a little bit, so I can move this a little further out, right here. And then I can place somewhere here, as they're asking me, a series lambda element, okay? That I will call it JX, which then is gonna cancel the J minus J100. That implies that when then I look here, when I look here, I need to see ZL, I need to see a total Z total, which is equal to ZL plus JX, and I want this to be 50 ohms. All right, so that practically, this solution is a very simple one. Just because The reason that it's simple is because the real part of Z naught is 50 ohms. All right, therefore that is because of this relationship. Otherwise, we could not do that. All right, so now if I continue along this thought, that implies that Z total will be equal to 50 minus J100, all right, plus Jx. And that implies that X has to be 100 ohms. Okay. Now, so I solved number A. I found, I have not exactly done this yet. Okay. Because this is positive, then X or Jx can be equal to J omega C. All right. And therefore, if I had given you also here F to be, say, 10 gigahertz in this case, and I would say in free space, everything. That implies that I know F, so J omega C will be J100, which means that C would be 100 divided by 2 pi F, and that will be in farads. And because F is 10 gigahertz, that becomes 100 divided by 2 pi 10 to the 10 farads. And from there, I find that C, I make this division. C is 100 divided 2 divided by pi equals 100 divided
So
by
do we have to use a capacitor?
Yes. Oh, capacitor. I'm sorry. Inductor. Why did I go to capacitor? I think my mind is somewhere else. Okay, so inductor here. Inductor, because it's positive. Capacitor would have given, I would give a capacitor if it were negative. Somehow I was thinking negative. So L in that case would be.
And there's one more JW or my omega C.
Yes, yeah. L. Thank you. And L would have been I think it is 15, 10 to minus 10, and it should be Henry. And it should have been, and it should be 1.5. So I take, yes, 1.5 nano Henrys. Okay, so move this one here. Move this here. All right. So we found here that L is 1.5 nano Henrys. All right. Then the next question that we have is what kind of a stub, a series stub. So we go to B. So now we want to change in B. This one, copy to this one, paste. All right, where now, since I have already done that, I will erase it. And then instead of that, I will put a short-circuited stub like this. But it's going to be out of section of a transmission line. So it's going to be like, all right. And then this here will be D, the distance, the length rather. The length of the stub will be D, and I will assume, because nobody has told me what the characteristic impedance of the stub is going to be. If they don't tell me, I will assume that this is Z naught, which is 50 ohms. You remember, if I don't specify the characteristic impedance, you're going to assume 50 ohms. For the stub, I did not specify, so you will assume 50 ohms. Okay, so now what I know is that this one here, the input has to be JX, the input to the stub. And then I know for a short circuited stub, so for a short circuited stub, and we have the Z input to the stub is equal to J Z naught of the stub tangent of beta D. And we know that this has to be JX.
Is that ZN? What's that over the N? Like ZN, what's that little?
That is the input to the stub.
Okay,
So
that just stands for like stub.
yeah.
Okay.
So let me write it here to be clear. Z input to the stub.
Is that equation only for short circuited stubs or open stubs?
So the general equation is the input impedance to any transmission line. So let's make a clarification here on how I found that. I don't want you to prove it there, but this Z in S is going to be Z naught for the stub, ZL for the stub plus J, Z naught tangent, beta D, Z naught plus J, ZL stub tangent, beta D. Where for short-circuited stub, so stubs, for a short-circuited stub, what do we have? We have that ZL, the load of the stub, is a short circuit, is 0. Okay, and therefore Z in S becomes, when ZL, we put ZL equals 0, and this one goes to 0, and then this one goes to 0, and this one cancels out with this one. So it becomes J Z naught tangent, and I would like you to remember that. Write it somewhere, put the most important formulas, write them on one piece, on one page to have them available. Okay, so this one is here. Okay, and therefore from one and 2, and from 1 rather here and 2.
Wait, so a short circuited stub has 0 impedance?
That's not 0. Z
Oh.
in S.
Oh, the right above it, ZL of stub.
ZL is 0, the load.
Uh,
The
that if
short,
it's shorted, that's because there's no current, right?
because it's shorted. ZL
Right.
is ZL of S, which means the load of the stub here. The load of the stub is 0 because it's shorted. Okay.
Wait, is that okay? When you say load, is that of the load or like the
No,
load of?
no, this is the load of the stub. This is the
Okay.
stub, and this is the end of it, which is shorted. So it's 0. But to find this expression here, you need to use the transmission line equations. See?
Right. Okay.
And in the transmission line equations, we have to put the load of the transmission line. So the stub is a transmission line that is terminated at the shore. This stub is terminated at the shore.
Okay. And the Z0 is the
characteristic impedance, which is 50 ohms.
of just the stub.
Yes.
And that could be different than the main one, right?
It can be different. But usually we do not make it different. We put it in it's most of what we do in this class will be the same Z0 with the main transmission line, whatever. I mean, unless the transmission line has a different, well, so for now it's 50 ohms. And as a matter of fact, I will specify it, make sure that everybody knows it in the midterm.
Okay, thank you.
Sure. Okay, so now from 1 and 2 here, from 1 and 2, we find that Z0 tangent beta D has to be equal to 100, all right? From which then we find the tangent beta D has to be 100 divided by 50, which is 2. And the inverse tangent beta D, therefore, has to be the inverse tangent of 2, which, according to my calculator, 2 inverse tangent in degrees is 63 degrees. Or if I do in radians, let's see, radians is 2 or, for some students do it one or another, 1.1, oops, 1.107 approximately rads. Okay, and that then gives me, I replace beta by 2 pi over lambda D, and let's make that rad, so it's 1.107, and then D over lambda is 1.107 divided by 2 pi. Let me write that better. And then, so if I take this number, divided by 2, divided by pi, that gives me 0.176 lambda. So that gives me that D is 0.176 lambda. And I'm good with that. I don't want to go any further. I don't have to. All right. So I found now, I gave answer to the second question of the problem. All right, so that was number B, not B. Okay, so now, any questions on this so far? I don't think so, since I don't hear. Now I'm gonna develop on the basis of this a problem, another problem, problem 2. I'm not gonna give you the same way the problems, even if the type of problems, I will try to decouple them. All right, so if you make a mistake in one problem, you don't make a mistake in every other thing that you do afterwards. So, but now I'm not gonna decouple them at this moment. So I will say problem 2. Problem 2. So now I'm going to the schematic that I gave you. Let me take this one. Copy. And I'm coming here, paste it. Okay. And now here, what I want to do is remove that, put the note here. Let me do this a little better. Or I'll put the note small. The note here. Okay. And then what I will do is to take this one and move it a little further out. All right. Take this one, and then connect this. Here, I will, well, first of all, let me take this and say, I will put a square around it. And I will call this a 2-port network. All right, so this is coming here and goes there. I will leave this out. So all of the Z nodes are 50 ohms. Okay, now I know L, I know D. So I will remember what we have. We have that L is 1.5 lambda. We found that D is 0.176 lambda. 0.176 lambda. Then we have Z naught 50 ohms. 50 ohms. And ZS 50 ohms. And F 10 gigahertz from the previous problem. So A at F equals 10 gigahertz. Find the power dissipated by the load. Load dissipated. Okay. And then I will continue with B. Second, find at F equals 10 gigahertz. Find the ABCD matrix for the 2-port Okay. All right. So I'll stop there for this problem. Okay, let's think about part A. At 10 gigahertz, we have matched the load to the line, to the 50 ohm line. Okay, so if I call this A prime, and I call this B prime, and I call this C prime, everywhere or anywhere on the line L that has length L. So as a result of this, anywhere on transmission line of length L, the reflection coefficient is 0. Reflection coefficient.
So in part, we just assume it's been matched.
Yes. This
Okay.
one is totally matched. All right. This together is 50 ohms.
Okay.
So this one is matched to this line. And because this one, all of this, is matched to the line, that implies that the reflection coefficient here, gamma, is 0. All right, gamma at CC prime. Let me see, draw it a little better. So at gamma at CC prime is 0. Okay, and as a result, it's everywhere 0 on the transmission line. All right, so gamma at CC prime is 0, which means that the magnitude of the reflection coefficient is 0 anywhere on the line. Okay. What does that mean? That means that the input impedance here, how much is it at this point? It's 50 ohms. Do we agree? It implies, therefore, that at F equals 10 gigahertz, where we have made the matching, Z input at A prime, which is this one, the purple, is equal to 50 ohms. Okay. If Z input is equal to 50 ohms, then we know that P input at A prime is going to be 1/2 the voltage at A prime times the complex conjugate of the current at A prime, or it's 1/2 V A prime, and instead of current we have V A prime divided by Z input, which is 50 ohms, all right? And all of this complex conjugate, which implies that this is 1/2 V A prime magnitude square divided by 50, and V, so there, but however, if Z input is 50 ohms and ZS is 50 ohms, remember ZS is 50 ohms, and Z input is 50 ohms, that implies that VAA prime is half of V sub S, because here we have 50 ohms, all right, 50. So we have that VAA prime is Vs divided by 2, which is 0.5 volts, which then implies that P incident at A prime, it's a formula that you have seen before, is 1/8 Vs magnitude square divided by 50, and that gives 1/400, and that gives point, let me see, 0, how many 3, 0, 25.
So Zn at AA is 50 ohms, but would it not be like 50? Oh wait.
It's 50 ohms, but the voltage that applies across it is half of Vs.
Does Zn at AA not include the Zs?
No, because
Okay.
it's all to the right of AA prime.
Okay.
So it's 50. That's the maximum, the optimal maxing. You remember the optimal matching of a source with an internal impedance is to make a load equal to the complex conjugate of the impedance, the internal impedance. But internal impedance is real. So the complex conjugate of 50 ohms, which is Z sub S, is 50 ohms, which is this, that what we made. And therefore, 50 ohms is the optimal matching. But if you have there 50 ohms, Vs splits equally between Zs and between your input at AA prime.
Okay. So okay. Isn't there a formula for like Zn? Like a
There is, but we made it 50 ohms at F with the matching network.
okay.
All right. So we have already done that. We have worked on the matching. Okay. So we found that this is 2.5 milliwatts. And because this is in watts.
Oh, on the PN, like power in at AA, why do we use the complex conjugate of the current?
Because the power, if you have any load, and then this is the voltage that applies across it. Not this capacitor, let me see. Let's assume that it's not a DC. And this is Vs. And the current that flows through it is IAA prime, and this is BAA prime. Then the power that is delivered to this ZL is 1/2 by definition. VAA prime, IAA prime complex conjugate. Okay, let me reconnect.
So like it's the complex conjugate because of like what reason, I
That's the
guess?
definition. That's the definition of power in the Fourier domain, in the frequency domain.
In the frequency domain? Okay.
Yes, that's the definition. Okay,
But if
definition.
we were in the time domain, it would just be regular current.
Yes. So
Or I
power
guess, yeah.
in frequency. Definition. Okay.
Yep, sounds good.
Therefore, from here we found that P that goes inside AA prime is 2.5 milliwatts. However, let's now think how much of that goes to the load. So all of these here goes inside the line. So practically inside the line here, we have P in, all right? So this is gonna be P in. But the line does not have any resistive elements. So if the P in is all real, and there is no any resistor between AA prime and BB prime, so all of it goes here. So all of this P in goes to ZL, which means the P in that goes to ZL equals 2.5 milliwatts. And since ZL has both a real and an imaginary part, that means that all of these 2.5 milliwatts are going to be absorbed by the real part of the impedance, which is going to probably be a resistor, all right? Because ideally what we know, so here I'm going to say that. So P in, which is 2.5 milliwatts, will be absorbed by ZL, where ZL is 50 minus J 100, which implies that ZL is nothing else but a resistor, which is 50 ohms, plus a capacitor, all right, which is C here, L, and therefore we have that ZL is 50 plus 1 over J omega C, which makes it CL 50 minus J 1 over omega CL. Means there is a resistor and a capacitor. And all of the real power that goes here, which is all of this is real, all right, power is real, is gonna all be absorbed by the real part, by this resistor. So all of P in will be absorbed by the resistor. Why is it that it's gonna only go to the resistor? Because The capacitor does not absorb real power, it only absorbs energy. And energy in the frequency domain is like an imaginary number, all right? So only all the real power is absorbed by resistors or by an antenna, for example, which is equivalent to a resistor. And instead of being dissipated in the resistor, it goes primarily, it is radiated if it's an antenna. But so all of the real power then here goes to this resistor. So that is the first one. Let's now, so we did this. We did this. Now let's try to go to B. Okay. We'll now take the same picture here. Copy. So go B. So B here. We'll put this here. And then we're going to clean it up a little bit. So I'm going to remove some things. I will remove this. We don't need that. I will remove this. Let's see, this one. I will put C prime here. I will remove this one. I will remove this. I will remove this here. And this one. I will remove that. And I will remove this. I will remove all of that here. Oops, okay, connect 1 second so I don't lose power. 1 second. So I'll put this one here. And one more thing I want to do, just a second. All right. All right, so now I will remove this for a moment because that's a load, I don't need that. And now I have this two-port network. And I need to find out the ABCD matrix. Okay, so now I'm going to what we saw before, and I will, let's see, let me go back for a second to this. Okay, so we have this here, network, and I need to keep that in mind. We're gonna use this for the ABCD matrix. So what we're gonna do, I'm gonna take a picture of it for a second, and then I will put it in, we'll add it. That's good. A moment. Okay. And okay, I mean, it's not clean. but I think we can see, no, we cannot see what it says. We can do this. 1 second, bear with me, because I don't know how else to do this. All right, let's see. Okay, I think that will be good enough. So let's see. We're gonna go back to what we have, and then let's see what I have. All the photos, not albums, all photos. Sorry, it says media. All photos. No. All right, it's not there yet, but we'll wait a little bit. Let me write down. So what we're gonna find from this, what we're gonna find out from this matrix that you may have in front of you is the ABCD matrix of smaller networks. So here, for example, one network that I will do, I will, let me cut this for a moment. So one network is this one, all right? Let me move this a little bit higher. The other network is this one. And the two together make the two port, which is this one. Okay, so the two port is this. And then you have two smaller networks within that. Now, we know, and that's very similar to the homework, that the network for this one, let's call that A, B, C, and D, green one. And the network for this one is A, B, C, and D. Okay, and then from...
Excuse me.
Yes.
We can see the screen.
Yes, thank you. Yes, sorry. Green. So I will repeat. Okay, so what I did is that I brought here, what we have to do is to find the ABC matrix of this two-port network, which is what I have in the big square, okay? And what I said is this network is made out of two smaller ones. One is the green, the one that is circled by green, which is a section of a transmission line. And the other is just a series short-circuited stub. And I have indicated the first one with green, ABCD in green, and the other is the ABCD in blue. Each one of them has its own ABCD matrix. And then we know that because the networks are connected, the green and the blue, then we know that the total. In fact, let me also do the following. So since I have the capability to do that, call that the red network, all right? So the total ABCD matrix for the two-port for the two-port is the product of the other two ABCD matrices. And then I'm going to write the equation below. So we're going to have that A, B, C, and D, the red, is going to be equal to the green with the order from the left to the right, all right? Whatever is closest to the source goes first. A, B, C, and D times the one next to it, which is this one. A, B, C, and D. So practically, if I find the green ABCD and the blue, the light blue ABCD, then the product of the two will give me the red ABCD, which is the ABCD matrix for the total network for the two-port. And now, from the book, we have that the ABCD matrix, which has 4 elements, A, B, C, and D, and is the matrix for the transmission line, all right, has, according to this, it has the following form: cosine of beta L, and then has J Z naught sine of beta L, and then it has J Y naught sine of beta L, and then it has D cosine of beta L. Okay. Now I'm going to find these two ports at F equals 0. Excuse me, 10, F equals 10 gigahertz. So at F equals 10 gigahertz, then we have that beta L is 2 pi over lambda, and L we found is 1.5 lambda, we were given, so that makes it 3 pi, okay? And then what do we know from there? That cosine of 3 pi is how much? Is -1, all right? And then from there we have that sine of 3 pi is 0. So on the basis of that, we have as a result that the A, B, C, and D equals -1, 0, 0, and -1. That's the ABCD matrix for that particular line. Okay, now let's find the blue one. So from text here, let me write it from text. All right, so again, from text on networks. What do we know? We know that A, B, C, and D for a series. Let me make sure that I'm correct. For a series short circuited stub is equal to 1 J Z naught tangent theta, where theta, I will write it, where theta is beta D, and 0 here, and then 1 here. All right. Now, how much is beta D? Where we found that beta D impact, I will write it here directly without even having to do that. You remember? We found J Z naught tangent beta D. What did we find? How much was that? You remember from up here? From this one? What did we find? That J Z naught tangent beta D is J100. All right, when we solve the problem. But if you have not done this, if you have not solved that problem, you will have to come to that conclusion by plugging in beta D and Z naught. So we can do that now. I will use, how much was D here? 0.176 lambda. So let's try to do that, all right? You see that it's gonna come out the same. Equals J 50, and then tangent of what? 2 pi over lambda times point, what did I say? 1.14176. 0.176. Okay, let me move it a little further here. And then that. Okay. And then we have lambda, obviously. I missed a lambda here. Lambda. And then 2 pi. See? We have 2 times pi times 0.176 equal, and then we have tangent of this, which is 1.99. Okay, this is kind of interesting. J50 times 1.993, just because I rounded up when we found D, I rounded up, and then that is going to give us times 50 times 1.993 gives us 99.67. So that gives us about J100, as it was supposed to be. Okay, so we have that to be in ohms, and therefore from there we find that A, B, C, and D here is equal to 1, J100, 0, and 1. So now I have 3 here and 4 here. And I can take the product of 3 and 4, and then I find that the total ABCD matrix for the 2-port, A, B, C, and D, for the 2-port is equal to, and we use a different color so people remember, 1, 0, minus 1, times 1, J100, 0, 1, and then that gives equal Okay, so we take this one times this one, and that gives -1. Then we take, oh, excuse me, the other way around. We take this one times this one, and it gives times this one, and gives -1. Then we take this one times this one, and it gives minus J100. Then we take this one times this one and gives 0. And then we take this one times this one and gives -1. And this is the ABCD matrix for the two ports. So the ABCD matrix for the two port is -1 minus J100, 0 -1. Okay. So these are two separate problems, obviously. I'm not going to give you both of them. I'm going to give you only one. But if it's the first one, then you will have to find the matching network, and then first of all with the lumped element, and then with the stub, all right, in this particular example. If it were to be this one, where you have to find the power dissipated to the load and then ABCD, then I would give that to you and say that you match it. For example, I will tell you, you have this network and the network is matched with these kinds of dimensions. And then I would ask you to do those kinds of things. So you would have that, and then you would have to calculate here. All right, so that is one possible type of a problem. Any questions on this? I will, okay, I think, wait. Okay, I'm sharing the screen. You see that? You don't see it. But I think I'm okay. I'm not gonna solve anymore. These two problems, I will print them out and put them as part of the review. I will have a new module that is called a review module for Midterm. And then also I will do this now, and then because that's easy. But then for the recording, I will be able to do it tomorrow, because I will have to download the recording, and then they don't download it immediately. So it takes some time for it to be processed on Zoom. And then I will have to take it there, clean it up a little bit, and then upload it on YouTube. And then I will put this tomorrow. Any questions on this?
No.
Okay. How did you find those kinds of problems? Are those like one? Let's assume that I give you one problem like that, 2 questions. How would you find it?
Easy.
Okay.
Definitely easier than the homework.
Well, the homework is not the homework is supposed to have you go and do more work. I will never give you anything like homework for a midterm.
Okay.
No, I would never expect you to do anything. Homework is practically an extension of the learning. It's not a test. It's not going to be like, I'm not going to give you something that you have not seen before. Homework is the only way for you to go back and look at the material and think a little bit, you know. That's why we give a week. Otherwise, I would have expected you to do it the next day. Don't do that.
Okay.
Okay.
Thank you so much.
You're welcome. So more on, so tomorrow is Friday, more on Sunday, all right? And then Monday again, because I think Monday most probably a few more people may come. But I will print it out anyway.
Okay, perfect.
Okay, take care.
Thank you.
Bye-bye.
Bye-bye.